Hello, my name is Christophe de Bruyne, and in this lecture we will cover how we can transform data contained in relational databases into RDF. What we aim to do in this lecture is transform the data contained in relational databases into RDF. In this example, we have two relational tables, person and city, and we assume that people are related to their city via city ID, which is a foreign key pointing towards records in the table city. What we want to achieve is the following. We want to state that these two records represent people and they are identified in some way, shape, or form. And those people have first names, last names. They're both of the type FOF person, and hopefully you recall that FOF is a vocabulary to describe people. And both of them are based near a particular city, one being Dublin and one being Ghent. The Relational Database to RDF movement, or RDB to RDF for short, all started with Tim Berners-Lee proposing a direct mapping language to transform relational databases to RDF. This sparked a discussion, and over the years, two W3C recommendations were published that specified how one can map relational data to RDF. The first one was a direct mapping of relational data to RDF, and the second one, R2RML, is a highly customizable mapping language that allows us to prescribe how data contained in relational databases needs to be transformed into RDF. RDB to RDF started with a blog post written by Tim Berners-Lee, where he discussed a set of mappings that can be generated automatically between relational databases and RDF. And you can find the post over here. In that post, he has written the following. The semantic web data model is very directly connected with the model of relational databases. A relational database consists of tables, which consist of rows or records, and each record consists of a set of fields. The record is nothing but the content of its fields, just as an RDF node is nothing but the connections, the property values. And then he proceeded to state the mapping is very direct. A record is an RDF node. The field, column name, is an RDF property type, and the record field, table cell, is a value. Now, indeed, it is not always that simple. Can you provide examples? Well, it could be, for instance, that in a relational database, you might have, due to normalization and reference tables being removed, you might have a subset of your relational table schema actually representing a complex type and not merely a value of a record field. We will see a couple of such examples in this lecture. Both W3C recommendations were published on the same date back in 2012. We will first cover the direct mappings. Now, it started with Tim Berners-Lee's blog post, where he proposed a direct mapping that immediately reflects the structure of the database. His proposal was refined into a recommendation. Now, in both instances, the target RDF vocabulary directly reflects the names of the database schema elements, and neither structure nor target vocabulary can be changed, so it's not customizable. He then declared the process. Existing table and column names are encoded into URIs, reflecting classes and properties. Then the data is extracted, transformed into RDF, and loaded into a triple store, which basically boils down to an ETL process: extraction, transformation, and load. This proposal, as I said, over time was refined into a W3C recommendation published in 2012, which you can find here. Now, in direct mappings, the database, both schema and data, primary keys and foreign keys are given to a direct mapping engine to produce an RDF graph. Fields are mapped to literals, primary keys are used to construct URIs for the resources, and foreign keys are used to construct properties and relate resources. For example, in this example, I will transform this very simple relational database into RDF. You can see that I have two tables, people and addresses. Both have a very simple primary key called ID, And there's a foreign key relating the table people to the table addressees via the column ADDR in people to the column ID in addressees. Before we can start the transformation process, the algorithm, as prescribed by the W3C recommendation, needs a base URI. In our example, the base URI will be http://foo.example/db/. The RDF that will be generated will look as follows. We will have our base declaration, and we will have a couple of namespace prefixes that will be useful for our example, such as XSD for the data types, RDF for RDF type, and so forth and so forth. Let's start by transforming the contents of the table people. What you can see here is that the name of the column was used to create a URI to represent the type. So this type has the URI http://foo.example/db/people. You can furthermore see that each column name was used to create a property. The URIs of these properties look as follows. Their URI contains the name of the table, hash, the name of the column name, and then the values are assigned to each instance. We also know that the column ADDR has a foreign key to the table addressees. For foreign keys, the properties that correspond with those get a URI that looks as follows. There's the name of the table, hash, REF for reference, and then the list of column names that constitute that foreign key. It will also point for each instance to the corresponding RDF resource. Now, how do instances get their URIs? Well, for each record, a resource is created, and the URI looks as follows. It is the name of the table, slash, and then for each column in the primary key, it will contain the name of the column, the equal sign, the value of that column, and if there is more than one column in the primary key, they're separated by a ampersand. You can see that null values do not result in RDF statements. The second table is a lot more simple because it doesn't contain many columns and it does not contain any foreign keys. But you can see that this one corresponds with this one. And that's how we generate our RDF graph. Now, the W3C recommendation, direct mapping recommendation, does prescribe how you need to deal with data types. For instance, we know that these columns, ID, addresses, or ADDR, and ID here, they're very likely of the data type integer. The direct mapping W3C recommendation provides a mapping of SQL data types to XSD data types. So in this example, which I have simplified for this lecture, you would see that this one would be data typed as follows, XSD integer. At this point, I usually start a small discussion with my students. I ask them the question, are direct mappings meaningful, and can you identify potential problems? Direct mappings are meaningful to those who know the database. In my example, I know because I own or develop the database that ADDR stands for the address. But that was still pretty straightforward. However, the foreign key did not state what the relationship was between people and addresses. Was it the address of residency? Was it the address of birth? Whatnot? We do not know. Other problems that we could identify include the groupings. It is very well possible that in our database we have a column that is reduced to a value that should be represented as a complex thing, something that is a resource with their own URIs and whatnot. Think of gender, or maybe even the city in an address table. Cities are complex things that can have metadata as well, assigned via RDF statements. To address these issues, another proposal was developed and published as a W3C recommendation over time, and that is the R2RML mapping language. R2RML, which stands for RDB to RDF mapping language, is also a W3C recommendation since fall 2012. They have been published at the same time. And they allow us to create an R2RML file that annotates a relational database with existing vocabularies and or ontologies. And they can be formalized using RDFS, all, and so forth. The R2RML file containing those mappings goes through an R2RML mapping engine to produce the RDF. The R2RML W3C recommendation does not only specify an ontology to specify those mappings, but also an algorithm that prescribes how those mappings should be interpreted to produce RDF. And this is pretty neat because the ontology provided by R2RML is a semantic web ontology. It is represented in RDF. Stored in an RDF, and the R2RML files are themselves stored as RDF. And this allows us to treat them as RDF as well, which means we can add statements with other vocabularies, such as provo for provenance information, metadata, who created the mapping, where did the mapping come from, and so forth and so forth, which could render the whole process a little bit more transparent and reproducible. But that's not the topic of this course. We will now be covering the mapping language itself. Let's start by creating an R2RML mapping for our simple example. We will now start with the table addresses because it's a little bit more simple. On the right-hand side, you can see that I have created an instance of a triples map. A triples map will contain all the directives to transform the information in a result set into RDF. A triple map consists of three things. First, we have the logical table, which can either be a table name, and the table name can contain names of tables or views, or an SQL query. We will see an example later on. That is mandatory. Otherwise, the triples map does not know what to transform. A triples map must contain a subject map. The subject map prescribes or tells the R2RML engine how to generate and state something about the subjects of those triples. In this example, we will generate for each row in the table addresses a resource with the following URI: http://foo.example/addresses/ and then we use values from the columns in the result set. We also know that each record corresponds with a place. We avail of the dbpedia ontology to state that each subject generated as such is of the class dbpedia place, resulting in a triple resource with that URI RDF type dbpedia place. You can have 0 or more class statements. Now, finally, a triples map can contain 0 or more predicate object maps. Predicate object maps, as the name implies, will generate for each row predicate and object combinations. We will see what will happen if we provide more predicate and predicate map directives and object map directives in a predicate object map. In this particular example, we will generate RDF statements using the predicate FOV name that will be related to each subject, and its values will be taken from the columns. And in this particular case, we will take the values for the object from the column city, and we will treat them as strings. In this case, it is implied. As I said, the logical table of a triples map can contain either a table name or an SQL query. Here you can see an example that is equivalent where I used a query to retrieve all values of ID and city from the table addresses. Now on to the next example. In the next example, we will create a triples map for people, but we've seen that there's a foreign key, so we can relate people to addresses, which we will cover here. Again, pretty straightforward. We have a new triples map, and make sure that you provided a different name node in the R2RML file. It has a logical table, people. It has a different subject map. Now I am creating instances of person, and I want them to be disjoint from addresses, so I have to make sure that their URIs are different. They're of the class FOV person, and I create a predicate object map, much like in the previous example for FOV name, but here I retrieve values from the column F name here. Now, how do I relate the two? Well, I will create a special predicate object map. In this predicate object map, I use the predicate FOV based near, and for the objects, I will inform the R2RML engine that he has to retrieve the values from another triple map. So the parent triple map is the addresses triple map that we created in the previous slide. Now the engine is smart enough to do a natural join if no join condition is provided, but in this case a natural join wouldn't work. So we provide join conditions, and we tell the R2RML engine you have to combine the two logical tables as follows. You have to match the IDs, the ADDR field from our triple map with the ID field of the parent triple map. And he will then generate a join, an SQL join, in order to create RDF statements for this particular predicate object map. Now, in this very simple example, we haven't covered what would happen if some values are null. If values are null and used in the mapping, then it will not generate any statement. We also didn't cover how to deal with RDF graphs yet. But given these two triples maps, the values, given these two triples maps, which are stored in one file, we now need to avail of an R2RML processor and an engine. You can find in other videos that I avail of one that I've developed. You basically provide all the things that are necessary, a connection URL, username, password, and so forth and so forth. The two triples maps are stored in a mapping file, and we tell the engine that it needs to generate turtle, and the output file is called as follows. You can find the video on my channel. The result is as follows. You can see that I have two instances of people, person 1 and person 2, and the first person is related with an address via the predicate FOV based near, and it's as simple as that. If you were to consult the R2RML W3C recommendation, you will see that the key concepts of R2RML are related as follows. We have covered most of them. We know that a triple map must contain a logical table, it must contain a subject map, and it must contain 0 or more predicate object maps. And each object map has a predicate map and an object map to help generate the RDF statements. There's a very special object map that is the reference object maps that requires join conditions. R2RML provides also a way to organize your RDF statements into named graphs. So a subject map and a predicate object map all can have 0 or more graph map statements. We will see later on what will happen if we use those. Here's another diagram from the W3C recommendation relating various concepts of the R2RML mapping language. There's this notion of a term map, which is the, let's say, superclass of the various maps, the various term maps that we've already encountered. We have encountered subject map, object map, predicate map. We have not yet encountered graph maps in an example, but we will see one later on. Now, term maps can generate values based on either a constant, a column, or a template. And I'm not entirely happy with how it is represented, because the constant value, if it's used in a subject map, graph map, or a predicate map, then it must be an IRI, it must be a resource. But if it's used in an object map, then its value must be either a literal or an IRI. And this gives the impression that it has to be an IRI. So the representation is a bit unfortunate in the W3C recommendation. Now, notwithstanding what you use, you can also assign term types to a term map. And you can state that it generates resources, named resources with RRIRI, or you can state that it generates blank nodes with RR blank node, and you can state that it generates literals with RR literal. And you can furthermore provide language tags and data types if you're generating literals. Finally, there is RR inverse expression. They are useful only when accessing relational databases as virtual graphs. They provide some sort of optimization hint, and I will provide an example of that later on. Now, RR class statements in subject maps. We've seen in the example that a subject map can have 0 or more RR class statements. Whenever the result set contains no null values for anything used in either the template, the column name, and so forth, to generate the identifier, either the URI or the internal identifier for a blank node, whenever that's possible, it will generate RDF type statements for each class appearing in the subject map. So for address 1, for instance, I would then have http://foo.example/addresses/1 RDF type dbpedia place. While there are nuances when combined with graph maps, this can be considered syntactic sugar for the following. So the subject map generates for each subject a triple with RDF type as a predicate and dbpedia place as an object. So in other words, in this particular case, RDF type and dbpedia place are constants. So can we generate or can we create a predicate object map with 2 constants? And the answer is yes. We just create a predicate object map where we assign the constant value RDF type to predicate, and we assign the constant value dbpedia place to object. So you can consider this to be syntactic sugar. But as I said, once named graphs come into play, it's a little bit more nuanced. Here we have another example of syntactic sugar. Whenever you use constants, you can ditch the predicate map and object map properties. So in this example, you see that we related RDF type to RR predicate and dbpedia place to RR object. And this is basically equivalent with RR predicate map with a value RR constant RDF type. And for the object, pretty similarly, we would have an RR object map that has the RR constant dbpedia place. This needs to be connected. So these two are equivalent. Now, what happens in practice? Something that I have encountered in a project or that other people have done to optimize the process. Now, the algorithm as prescribed by the R2RML recommendation states that for each triples map, it will generate a query for the logical table and will be applied to all the graph maps, subject maps, and predicate object maps that do not refer to another table. So the result set of this query will then be used to generate RDF for this subject map and this predicate object map. For the predicate object map maps that refer to a parent triples map, a new query will be generated based on the join of the two logical tables. So in order to generate RDF for this predicate object map, it will take this table name and the table name of addresses and do a join based on these join conditions. Whenever you have very large databases, this could slow down the process. However, if you know what you're doing and all the information to generate these links is contained in your child triples map, then you can, between quotes, bypass this process by creating a regular predicate object map as follows. You copy paste the template or column value or the template, whatever, of the subject map of your parent triples map and you place it in the object map as follows. And you obviously need to use the column names from your child triples map. Now, this will work only when you have a correspondence. For example, if you were to have a value in the people's table that does not appear in addresses, well, then you will generate a resource, but there will be no information provided to that resource via the addresses triples map. That is obviously not going to happen if you have a foreign key, but if you have databases where you don't have foreign keys, but some things can be joined, however there are missing values, well, you might end up with an RDF graph that is not equivalent to the graph that is generated if you would have used the parent triples map. Now, graph maps. Graph maps may seem a bit daunting, but they're pretty simple once exemplified. So graph maps can be assigned to subject maps and predicate object maps, and they both can have one or more graph maps. They are specified in two ways, either by assigning a constant with the property RRGraph, or by providing a graph map that returns RIs, so named resources. There is if you do that, then you have to use the RRGraph map property rather than RRGraph, similar to the example we've seen before for RR predicate and RR predicate map and RR object and RR object map. There's a special named resource called RR default graph for the default nameless graph. Now, if a subject map has no graph maps, then the set of graph maps is RR default graph. If both the subject map and a predicate object map have no graph maps, then the set of graph maps is RR default graph. Otherwise, it is, for each predicate object map, the union of both graph sets. Sounds complicated, but it's not. Let's exemplify. In this example, we see a subject map, a predicate object map, and a predicate object map that uses a parent triples map. It's the example from the previous slide, and I have divided them into 3. Now, what happens if I execute this mapping? Well, all triples generated by the subject map will be entered into the default graph, and the same for the first predicate object map and the second predicate object map. Now, what would happen if I assigned a RR graph statement to the subject map and it refers to the RR default graph? Well, that doesn't change anything. Triples generated by the subject map will be stored into the default graph. The triples generated by the predicate object map, the first one, will be stored in the default graph, and that of the second predicate object map as well. Now, what will happen if I assign a URI to the RR graph statement of the subject map? And in this case, I give it the URI fragment 1. So for simplicity, this is the first named graph. Well, obviously, we will have a named graph of that URI, and all the RDF statements generated by the subject map will be stored in that named graph. Funnily, however, the triples generated by the predicate object maps will also be stored in that named graph. Why? Well, if no graph statements were provided for the subject map and the predicate object map, the default graph is the default graph is the default graph. That's funny that it rhymes. However, the W3C recommendation states if either has a value provided, then it's the union. So the subject map has an RR graph statement. Therefore, it is not the union of RR graph number, the first name graph and the default graph. There's only one. So all the triples generated by the predicate object maps that have no RR graph statements will be generated into the RR graph statements of the subject map. Let's make it a little bit more challenging and assign the subject map and the predicate object maps each different graphs, and hopefully that will make the rule a little bit more clear. So in the subject map we still have our one named graph, so the triples generated by that subject map will be stored in that named graph. The first predicate object map has an RR graph statement pointing to another named graph, number 2, so there will be a second named graph, and the triples generated by the predicate object map will not only be stored in number 2, but also in number 1. Remember, the rule states the union of the graphs of the subject map and that of the predicate object map. The same holds for the second predicate object map, where triples will be stored not only in the third named graph, but also in the one provided by the subject map. In the final example, I want to exemplify 2 things. First, a predicate object map or a subject map can have 0 or more RR graph statements, and here you can see 2. Secondly, I wanted to demonstrate what would happen if you assign another or the default graph to either the subject map or the predicate object map. Well, in this particular case, for the subject map, nothing changes. All the triples generated by the subject map still go to the first named graph. For the first predicate object map, nothing changes either. The triples will be stored in the second named graph and the first named graph. The second predicate object map refers to both the named graph number 3 and the default graph. So they will be stored in 2 different graphs. And they will also be stored in the named graph referenced by the subject map. Now we will cover some quirks is not the right word, but special things about the R2RML language that people might struggle with, but they're all described in very much detail in the W3C recommendation. There's a couple of implied rules. So we know that R2RML supports mapping values with constants, column values, or column values applied to a template. Now, if an object map does not refer to a column, or has no language tag, or has no data type tag, then the values default to named nodes, unless you explicitly specify it to be a literal. So in this particular example, had we not provided this directive, the R2RML engine assumes that for this particular predicate map, using the predicate FOV name, you will generate a named resource using the combination of these two column values. And we know that this is not a valid URI, so it will break. This will provide an error. But if you use a template directive for an object map, and you want to use a template directive to generate literals, then you have to tell the engine that. You have to state, I am generating things of the term type literal. Now, when you create term maps with the term type literal, and that can only be the case in the object map, you can assign them a language tag. So in this particular example, we state that this predicate map generates RDF statements using the predicate label, RDFS label. The values will be fetched from the column title, and they will receive the language tag EN. So this will generate triples with the following object title. So let's assume the title is foo, and it will then generate a language tag EN. Now, asking the question, why is the above term type implied to be a literal? Well, it is implied to be a literal because we avail of the RR column directive. If we use column, the R2RML engine will assume that we're fetching values. It uses a column. It is not uncommon to find in relational databases tables containing values with its translations. So you might have a particular ID, a language, for instance Dutch, and you would have Brussels, and then you would have another record for the same thing, and you would find that the translation in French would be Bruxelles, and so forth and so forth. Unfortunately, R2RML has, in my opinion, poor support to basically state, well, use this as language tag for that in a dynamic manner. What can you do? Well, if you have a table of multiple languages and you have some sort of discriminator, as you can see here, then you can create a logical table for each of the languages that you have. So you would then state, okay, select all the values for which the language corresponds with NL, and then another one, another triples map for the French values, and so forth and so forth. Another approach would have been to create one logical table and use the language column to create a single mapping for all languages. However, that is not part of the recommendation, and support for it depends on the implementation. So there is a extension, if I'm not mistaken, proposed by Catherine Faron-Sucker and her PhD student, that created an extension that allows for that. So you can state the language column is provided here. Now, unless you use one of these extensions, you cannot avail of set functionality. But another problem with an extension is that you then create mappings that are beyond the standard scope, so they become less interoperable. Now for data types. Data types can only be declared for term maps that are of the type RR literal and are without a language tag. So you either use a language tag or a data type, but you cannot use both. Obviously, those term maps are only object maps. So in this particular example, we have an object map that refers to the column no employee number, and we assign it to be of the data type XSD positive integer. You are not only limited to data types of the XSD namespace, you can avail of other URIs. For instance, from GeoSparkle, GeoWKT, literal. That's one example that on top of my head that I'm aware of. Now, again, to reiterate, why is R2RML so powerful and flexible? Well, it allows you to avail of projections and selections in your queries to generate RDF. What do I mean by that? Well, let's assume you have a table and you have multiple columns, you have multiple rows, and it can be that you have a couple of columns inside your table that represent a concept. I will use a different color. So that grouping may represent an instance of a class that is related to the instance of another class captured by the rest of the records in that table. A good example would be a city. A city is often a column in a table addresses, yet cities are instances on their own. So you can create a triple map for what we call a projection of a table. Similarly, you can map selections. If you need to create a separate triples map for cats in your pet table, you can do so, and then you only select a couple of or a subset of the records, and then you can create a triples map for fish if they have different properties to cats, and so forth and so forth. At the beginning, I stated that I was going to say something about RR inverse expression. RR inverse expression was used for when one is dealing with virtual graphs. In other words, you're retrieving RDF by translating the Sparkle queries into SQL queries via mediator. So the R2RML mapping is used to generate SQL queries on the fly. Now, R2RML transforms database terms into RDF terms. The inverse expression helps one to transform RDF terms back into database terms, which may increase performance. I am not aware of any implementation that supports or implements this, as it is not necessary for R2RML views to be generated and work. It's a optimization technique. So let's exemplify the use of RR inverse expression. First, I assume I have a database and a table where all surnames are stored in capital letters for this example to work. Now, obviously, well, not obviously, in my example, I want to generate URIs for people, but I'm not going to use the capital letters. So I have a triples map where I create RDF statements about things based on the following SQL query. I avail of the email address and I transform the values of surname into lower caps and I assign it to the variable elsewhere. Now the subjects have the following URI structure, http example.org/person/ and then the lower cap value of their surname, and I assign their email addresses via the both box predicate. Now, what will happen if I fire the following query and I ask, give me the email address of that particular person? Well, the SQL query for retrieving the value of an email address should correspond with select email from employee where the lower cap representation of the surname equals de Bruyne. And this may be very slow. Now, that is in the case when we use this mapping to access the database as a virtual graph. So on the fly, this Sparkle query is transformed into that SQL query. This particular one can be very slow. So how can we optimize that? Well, with the RR inverse directive, we can state that the surname needs to equal this following transformation function. So whenever we fire this query, this will generate the following query. SQL query, select email from employee where surname equals upper de Bruyne. And if surname were to be indexed, this query would be much, much faster. So that is the use of our inverse expression. It potentially optimizes the retrieval of information when accessing the contents of a relational database as a virtual RDF graph. So how can you use these R2RML mapping files? Well, you can use them to translate the data into RDF, which are then subsequently stored into triple stores for consumption. The downside of that is that it will be harder to maintain updates. So if your database evolves over time, you have to make sure that those changes are propagated to your triple store. Triple stores, there are many you can avail of: JanaTDB, Virtuoso, BlazeGraph, and whatnot. As we've seen with the inverse expression, you can also use those mappings to access the the database as a virtual RDF graph. And whenever you formulate Sparkle queries over the RDF, well, they're changed into intermediate SQL queries. So the advantage is that you have at any time the most up-to-date data, but the execution of the queries might take a little bit longer. If you were to follow the course on open information systems at the Vrije Universiteit Brussel, then the teaching assistant will demonstrate how you can use OnTop to mediate between ontologies and the database via those R2RML mappings. So this brings us to the end of the lecture. To conclude, we've covered the two W3C recommendations for transforming relational databases into RDF, one being the direct mapping that reflects the structure of the database, and the other more flexible and extensible approach being the R2RML mapping language. What we haven't covered in, or what I haven't covered in this video lecture, are some of the more recent initiatives proposing extensions to the mapping languages in order, for instance, to cope with functions and other types of data. But you can find those in the PDF version of the slide deck. I welcome you, or I encourage you to consult my YouTube channel, where you can find a video of an R2RML tutorial, a step-by-step R2RML tutorial with sample data, so that you can get better grasp on the material that we've covered today. Here are a couple of references that I've used to write this video lecture, and I wish you the best of luck in creating RDF from databases.